have, suppose you have some data, and in the data, you are not able to predict the relationship or predict the existence of the data or the possibility of the data to come in the future. Like it's highly non-predictable, but you have some kind of event that is happening. So immediately, the Markov chain means we have to imagine the phenomena of a random walk. You never know in which direction the event progresses, your walk progresses, your move progresses. Okay, you can come back, or you can go forward, or you can stay it, or you can go with the off status, whatever it is. Okay, so why these people are using this is most of the Markov chain, they are going with the probability of finding that event. Okay, so one such small example is like, suppose, we have to design a Markov chain to predict the weather of tomorrow. The issue is now we are thinking about the future using the previous information of the past few days. So you don't know, because this is, you are going to only predict. This data is not with you. You are going to guess something. But what is the condition? But you should have some previous knowledge on the past events. Okay. So you are going to generate one model. Okay. So for example, suppose if it's a weather, the most thing is that it can be sunny, it can be rainy, it can be cloudy. These are the variants, correct? Sometimes we may see sunny, a day may be sunny, a day may be rainy, a day may be cloudy. But even in a day, sometimes it is sunny, sometimes it is rainy, sometimes it's cloudy. So this is a event which is really not able to predict by you. But you are going to observe the pattern of these three variations for some period, probably 1 week or 2 weeks or something. Okay, so our model should have three variants, which is just determining our future prediction. The future tomorrow can be sunny. The tomorrow can be rainy.
Excuse me, ma'am.
Yes.
Ma'am, sorry to interrupt. Are you presenting?
Are you? Sorry, guys. Okay. Sometimes I really don't know why it is happening. Sorry, ma. Okay. So I'm only talking about this slide, first slide. Okay. So we are talking about the Markov chain, how it is being useful in the weather prediction. Okay, so we are going to use a Markov chain to predict the weather of tomorrow. And we have to generate one model for the prediction of tomorrow's weather. So weather means we can think about three options: sunny, rainy, cloudy. Okay, so we have to generate one model which has these three variants, S1, S2, S3. Now, we have to understand whether the transition from sunny to rainy is there or rainy to cloudy is there. So, we have to establish a relationship between the variables. That is the transition probability. Okay, so we have to generate a transition probability between the variables, and we have to collect the data. But this, we are going to establish a new relation for the tomorrow based upon the previous day observation. Okay. For example, see this picture. What is this picture? Okay, this is the probability of the day to be sunny. If today is sunny, if the sunny to be retained, the probability is 0.8. Okay, now you see there's a transition from sunny to cloudy. Okay, so what is this? 0.15. Okay, then there's a transition from sunny to rainy. That is 0.05. So this is 0.2, 0.05 plus 0.15, this is 0.2, and this 0.8. So this is from Sunny, the transition is taking a probability 1. So this is the partial probability for the transition, and this is the state probability to retain it. Same, this cloudy. To retain this as a cloudy, it has a 0.5. But from cloudy to sunny, it takes 0.2. And from cloudy to rainy, it takes 0.3 probability. So altogether, 0.2, 0.3, 0.5, again 0.5, it is 1. So you see, when this probability is 1 and it is on. When there is no probability, it will not exist. Here also the same, rain to rain 0.6, this is one such example. So our worry is the same state to retain and the transition from one state to another, one variable to another. So we have to consider this. Okay, so this is what it is being expressed. So we know the yesterday was sunny, and what is the probability of having today as sunny? This is 0.8. Okay, from yesterday it was sunny. There may be a possibility of today to become a rainy. That is 0.05. That's what I explained. Okay, let us have all put together. It is 1. Let us see what is now. Let us say we have a sequence of observations. Sunny, rainy, cloudy, cloudy, sunny, like that. Suppose we are observing for a couple of days. In a day, we can be in any of these states, correct? So even this combination can be anything, any of the 3 states, even in a day. So we can use the sequence of the events. That is, following state sequence. Sunny is a state, rainy is a state, cloudy is a state, and this is the sequence. So this is a state sequence. So let us say this Q1, this is are having a state sequence which Qi that belongs to main 3 states. So now, in order to compute the probability of tomorrow's weather, we can use the Markov property. What is the Markov property? This is a probability of all the events, that is Qi, that is Q1 to Qn. The probability of this event can be this. That is, it's a multiplication because today's state is connected to the previous state. It is highly dependent probability. So it is a multiplication. What is that? This is the today event. This is the yesterday's event. So when I takes 1 to n, that is present state and the previous state. So knowing the previous state, you are going to observe the present state. But we have a sequence that is 1 to n. That's what we are taking a product. I is 1 to n. So this is the Markov property of identifying a state sequences describing the weather prediction between 3 variables, sunny, rainy, and cloudy. You understand?
Yes.
Yes. Yes. Now, the same equation, we are going to write it. Okay. So you see that I minus 1, knowing this I minus 1, you are understanding I. Now, we are going to use the same property there. Given that today is sunny, what is the probability that tomorrow is this thing? So, we have today is sunny. The possibility we can have another Q2 and Q3. How we can split it? First, knowing this Q1, whether there is a possibility of Q2. Knowing this Q1 and Q2, where there is a possibility of Q3. So this is a normal probability distribution, right? We have, okay, one known condition and we are working other 3 conditions. So what is this? Let us have this. Q1, Q2 and Q1 as it is. But now, if you apply the Markov probability, what is the main Q1 Q3 is the present state and Q2 is the previous state. We will not worry about Q1 and Q2. We will directly take the Q2. Understand? So what is the probability? What is this Q2 and Q1? So sunny to sunny. And Q3, rainy to sunny. Okay, so Q1. Okay, what is this sunny to sunny? Let's say that is 0.8. What is this rainy to sunny? So rainy to sunny, this is 0. I think, sorry, from sunny to rainy. Okay, so sunny to rainy, this is 0.05. So your probability that you generate, okay, so that is, you should know the statistics of being retaining the same state as well as the transition state. Okay, so you have a 3 variable and you are known with something, and your previous state, either it is a sunny or it is a, so tomorrow is sunny. So having the probability, today is sunny and tomorrow is sunny. So today is Q1, tomorrow is Q2 sunny, and the next day rainy, that is Q3 rainy. Okay, so Q1 is sunny, Q2 is sunny, Q3 is rainy. So Q1 is sunny, Q2 sunny, and Q3 is rainy. You understand? So from this equation, you should write the sequence: sunny, rainy. That is Q1, Q2, Q3. You understand?
Yes.
Yes, sir. Okay. Now, this is another. Assume that yesterday's weather was rainy and today is cloudy. What is the probability of sunny? So Q1 rainy, Q2 cloudy, Q3 sunny. The same equation. So once we know that Markov, if you use this, okay. So we have known two things. We already know today Q1 and Q2. We only want to know the future. That is your sunny. Okay. So Q3 divided by Q2. So sunny divided by what is Q2? This is the cloudy. What is this? Being from in the cloudy, how to have a transition to sunny. So from cloudy, it is taking a transition to sunny. What is this? 0.2. Understand? This is a transition. So this is the prediction based upon the conditional probability. Okay. I explained that time, no? Last class, conditional probability. You also agree with this? So now we are coming into what is this Markov model. I'm just generalizing. A Markov model is a stochastic model. A Markov model is a stochastic model which models temporal or sequential data that are ordered, because we will be observing in a continuous manner. So this has some order. It provides a way to model the dependencies of the current information with the previous information, that is conditional probability. We can always go with the current information with the yesterday's information or previous information. Definitely this has a dependency. It is composed of, what are the states? It is composed of states, transition scheme between states, and emission outputs. That is what, see, now we have transition state, one-to-one transition, being in the same state. Let us put one input and output. Okay, this is the, what is the, this is what a Markov chain, with an example. Okay, but now when we are going with the Markov property, if this is until now, this is a Markov. Now we are going to have one input and output. That is, I will show you. So, like this, okay, hidden Markov model. So we have to put some input and output. This is the difference. I'm coming to this. Let me read this. So it consists of, so outputs are discrete or continuous. That depends upon the data what we are handling. So the several goals can be accomplished by using Markov model. This is some example. Statistics of sequential data or prediction or estimation, or we have to understand some patterns in the given data. Okay, this is mostly people, most of the mathematical people, statistical people, they use the Markov model only. Now, what is hidden Markov model? Okay, so this is Markov model. This whatever we are seeing. Now we are talking about hidden Markov model. A hidden Markov model is same stochastic model where the states of the model are hidden. Each state can emit an output which is observed. Okay, every state is hidden, but it is giving an output which that output only is visible to us. Okay, the hidden states are all the possibilities it will work out, but it should give out the output what we are really observing as an event. Imagine, okay, now again we are imagining. We will use the same scenario to imagine the hidden Markov model. If you travel along with my explanation, you are locked in a room for several days. Okay, you have no connection, no windows, nothing. You are completely isolated from your environment. Okay, and you are asked about the weather outside. No people will talk to you, no phone is available, no clock is there, no TV is there. You are inside a room. Okay, now somebody will ask you, what is the weather outside? The only piece of evidence you have is whether the person who comes in the room bringing your daily meal is carrying an umbrella or not. Okay, so you are isolated in a room, somebody will bring your meal, that's it. But you have no connection with the environment, but you have to judge from the person who is entering into your room, who is bringing your whatever needs. Okay, so thing is that question is about the outside, and you have nothing with you to predict, but only your some message is coming through the person coming inside your room. So things are, what is the hidden matter here outside which is not known to you? Either it is a sunny, a rainy, or cloudy. What you can observe, that is what you can see, whether the person bring the umbrella or not. Even it is sunny, he will bring umbrella. Even it is rainy, he will bring umbrella. Then again it is a confusion. Okay. Now let's see. So Markov chain, we have already seen this. Now how we are making this as a hidden Markov model. Now see, so outside, okay, if this person, okay, coming with the umbrella and not using the umbrella, and is cloudy using the umbrella, not using the umbrella, using the umbrella, not using the umbrella. Let's say the same one, but with this, the person can predict if he comes, okay, possibility is there. If he comes cloudy also, he can carry, because with the guess that anytime it may rain. So what we are doing is, we are getting one emission event, one output event, which is observed, right? So let us assume that the t days has passed. Therefore, we will have an observation of the sequences. O in the sense observation. The substates, the sequence of the event is O1 to OT. Where OI is, what is the variable observation? Either the person is coming with umbrella or not umbrella. That is what you are given variable. Now, each observation comes from an unknown state. Where if unknown state, what is that unknown state? It is a rainy, sunny or cloudy. So, therefore, we will also have an unknown sequence, that is capital Q. This is observation. This is hidden variable. That is small q1 to q2. where Qi belongs to sunny, rainy cloud. So what we would like to know, the probability of all these events with respect to this observation, only known as this, you are going to predict this. Now, let us see. Last class we studied the Bayes theorem. What the Bayes theorem? Knowing this, you are going to understand this. Okay. So what is this? This is the probability you should know multiplied by, after knowing this probability, you will understand this. Or either way, you should know this probability, or knowing this probability, you should understand the OI. So both the sides, we will be having so a conditional joint probability. Okay. Now we are worrying about founding this in a sequential way. So this is the equation by Bayes theorem. So we are now expanding what is this I, because we have to have this observation for a couple of time. So there is a length of time observation. So this Q1 to Q3 and O1 to O3. So you are explaining everything here. The same equation, you are replacing this Qi divided by a sequential events that is observed for the last couple of days or whatever the previous events or whatever. Now, how we are going to replace this parameter for this? Okay. What is the Markov probability for this? See, now I am writing only for this. Okay. Markov probability multiplying all the states and with a known only the previous state. Okay. That is not taking I minus 2, I minus 3 or whatever. Okay. Only the immediate previous state. So this is fine. What is the independent observations assumption say that? Okay, now this is what this point. Okay. If you use that independent observation assumption, again, it is a collective way of writing the same, right? So it is collective way of writing P of OI divided by QR. Okay, so I is equal to 1 to n. Okay, so you can replace the equation. Okay, instead of this they have written the proportionality because there is also a dependent one. So once you know this, means it is understandable, you should know this. So instead of this equation, they have put the proportionality. Okay, the proportionality, the same equation is proportional to the multiplication of these two factors, because it is a multiplication. Again, they are multiplying these two. Now we are getting a product terms, two terms. One is transition from Q state to OI, transition in the same state from the previous day, retaining the same state from the previous event to this event. So now whatever parameters we have, these are the hidden Markov model parameters, that is transition probabilities. That is P of Qi divided by Qi minus 1. Then emission probability, because we are getting some observation, okay, based upon the hidden thing, we are getting some observation. So this is our emission. This is the what we can feel it. And what is the initial state? That is normally, this is the, okay, this is your initial state. So Q is the initial state. So the initial state probabilities we know. Then after knowing this initial state, we should know the emission probability and the transition probability to retain the same state. All the three information put together, if you generate a model for the sequential events, that is the hidden Markov model you generated for the particular parameters or the variables. Okay, you understand? I will ask you write down the hidden Markov model equation and explain the probabilities involved in this. There should be some question. Yes or no? You guys
Yes,
are on that?
Yes, ma'am.
Okay.
Yes,
Okay.
ma'am.
Okay, so this is the equation, but we can also generalize the same equation. That is, a hidden Markov model is governed by the following parameters. That is, A, B, pi. That is the transition state probability of a matrix A. It's a huge matrix. If it's so, we can put it in a matrix form, and let us say this is A. That is the state transition probability. Okay, then the emission, observation or state conditional output. Okay, because the conditional output is based upon the prior knowledge of the probability. So the prior initial state probability is the phi, and the transition or the observation is the B, and the single state transition is the A. All put together. If you are able to make a model, and that is your hidden Markov model. And now determine the fixed number of states n. Now we have to the another issue is like how many substates which is having one. Suppose you are having one matrix and you are having some substates. What is the possibility of upcoming with the observation S1, S2 like that. So it goes like that. So again, the state transition probability. Here we are talking about 1 minute. I'm just coming. Now, what is the state transition probability? Okay, so when I say this is matrix, normally it comes like this. So you all know, right? A1, first one will be A1, then it goes varies. From here, A1, 2, like that, this 1, 2, like that, it varies. So it's a ANN. Okay, so you have to have each row and every probability should be 1. Okay, so the condition is from one state to another state, there is a transition probability Aij. That is what it is A11 like that. So it's just transition probability. What is the emission probability? A state will generate an observation. So every observation is the output. That is the emission. But a decision must be taken according on how to model the output. So the one's observation is the output, but we have to design a model based upon the emission probability. As we said, the output can be continuous or discrete. Okay, and this is some of the discrete state. Discrete are the thing we don't want. Let us not worry about. What is the initial probability? So now you know that here are the probability of starting observation sequences. This is one sequential continuous event. We can put it a column, no problem. So this pi I is equal to a probability where all your Qi is your Si, because Si has n number. Pi I, that is this I is varying from 1 to n. All put together, the state will give you 1 only, because these are the substates. Okay, so this variable that goes with your number, how many data, whatever it is having. So one state may adopt and S1, S2, S3 like that. N number of states can have this probability. Okay, same transition probability. Yes, I can have a same transition probability. Yes, sorry, S1 can have a same transition probability. S2, like that, this pi I changes. Si changes, accordingly the pi I changes. So this is some such examples. Hidden Markov model. Here you see there's a coin and a die. So sorry, let us see this die. State 1 red. You have 1, 2, 3, 4, 5, 6. You have 12. 1, 2, 4, 6, 8, 10, 12 states. Okay. So this is like a head to red coins, and this is like a red coins to tail. Okay, head and whatever coin, because one we consider this as a head, the other we consider as a tail. So this is head to green to head. Okay, so every transition, if you put some kind of probability, like what we put in the previous table. So you can make one matrix. Okay, so you can make one matrix and you can write down this one. So this is a transition from head. This ordering you should make it. Any of the ordering with a known observation, you can make it and make a matrix. This is what. Then now I think in the vertebrae algorithm, I will not touch because today I will just give you the basics overall, because at least you should be able to write the short answers. That's what I'm planning. So state sequence decoding, these and all no need actually. Only I wanted to do the vertebrae, but now I will not do it because it is little more extensive. Okay. So now I'll give at least 5 minutes break, and next I will go to another thing. Okay, is that okay? Because I'm getting my throat pain. I'll take some 5 minutes break. Okay.
Okay.
Okay, ma'am. Okay.
Hello, shall we start, ma?
Yes, ma'am.
Okay, ma. So, now this is again going to be an introduction about the DNA. How many of you know about the DNA? You all know about DNA, right?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So, what is the structure?
Ma'am, double helical structure.
Double helical structure. And what are the components?
ATGC.
ATGC, right?
GC.
A will form 2 hydrogen bonds with the thymine, and guanine will form 3 hydrogen bonds with the what?
Cytosine.
Okay. So we have a AT and GC. Okay. So it is a ribbon-like structure which is forming a helix, and it has a groove, and every what is that, from pitch one space, because of one turn, complete one turn, we say it's a one pitch and one helical turn. And we have a major groove. This groove, the big one is the major groove, and this one is the minor groove. Okay, this is the structure based information. Okay, but now the problem is, like, you should know how this biochemical issues of this DNA, why this DNA is being again used to replicate the model. Okay, because I will show you some slides why people are thinking that the DNA can be, the structure of the DNA can be used to again make a computational model. What is the characteristics? I think, okay, so parallel processing processes all possible solutions simultaneously. What kind? Because everything, whatever you are doing now, is being recorded in the DNA, right? Okay, recorded means, see, intellectual ability changes, our physical behavior changes, the way we receive information changes, the way we respond to the information changes. All these informations are being stored. Okay, if the ancestors are good enough in some kind of technology, because if you see from the ancient time, a person who is in the astrologer, that family will learn the astrology easily, and the descendants will also follow the same job. If a doctor family, the grandparents, if a doctor, it is easy for the son or the grandson to capture the medical line easily. This is how, because the genetically whatever you do now is being recorded. But whatever is recorded now, it is not necessary to express immediately, but definitely there will be expression, but the expression will take some duration. Okay, we will be getting the expression, that is all the data, writing some information. The data is something, so this is because of this storage information. The DNA is able to store information. People are trying to replicate that memory disk with respect to the DNA. Okay, so now once we compare this, the DNA can copy things and it can replicate it. Okay, so many things, right? So about the DNA. So every time some iterations is there, some replication rate. So it is like how many seconds? It is like a megabyte or gigabyte or whatever they are trying to convert. And how about the data density? The DNA is so fortunate to have only these 4 variables. So spaces, like every nanometers is required. So in one dimension, you can have 18 bits per inch, and in the 2 dimension, over 1 million gigabytes per square inch. So this has some kind of fascinating features to consider this as a storage. Okay, so people start using this DNA. Okay, DNA for DNA computing. And they are trying to use this as a storage device. And perhaps, just few minutes, I think this one, a few minutes, huh? I'll just stop presenting, I'll go to another folder. I'll just connect now. Few minutes, give me a few minutes. Actually, I was searching for this article, somehow it's missed it from my regular folder. So I will post this article in the website. So what this talks about, the salient features of DNA and why it is being used as a computing this thing. Okay. So this is a general introduction about the DNA structure. Okay, you can talk about nucleic acid structures, sugar, phosphate group. See, these are all the things you know, I suppose, right? Hello?
Yes, ma'am.
Yeah. So I'm just simply giving an introduction because I need this content that you guys should learn this. So phosphodiester bond, hydrogen bond, everything is known to you. And the principle and processing of DNA computing, why means they are discussing some, see, you can synthesize some polynomial strength, right? What does it mean? They have explained the biology. But the thing is that you can be able to concatenate the information, similar to this synthesizing. Mixing means you can go with any combination of your events, okay? And annealing means like you can make a bond or you can come to any conclusion with any, shortcut. Annealing means you have to, in reality, you talk about, you heat and you annihilate and you never regain the structure. And melting is like it is going with beyond your, what is that biological condition. Okay, so these are all the things which has been, equally imagined in a mathematical way. So what happens is amplification is copying. So you can copy the data. Like if you are able to use one template, from that template you can go with another. You can synthesize or you can copy it. What is the separating? Separating means you can go with the subtraction, which is taking off the data. Okay. And cutting means for a long event, you can choose your own segments. So ligating means you can fuse two sequential events. And substituting means definitely like you can go with the substitution of your data with one another. Okay, so these are all the things like biological terms it is explained. So all these things makes the DNA as a equally able to do the arithmetic operations or whatever like in the artificial learning process. Okay, so the DNA computing, and you can also use this in the Hamilton path problem. What is the Hamilton path problem? When we say there is a path problem is definitely your graph comes. When there is a path means definitely there is a direction comes. So it's a directed path. So what the transition between all the four variables using this graph theory, again, like you can go with the same, what is that, Hamilton path problem, explaining, because once your graph theory is embedded, and the probability of becoming the evolution from adenine to guanine to cytosine to thymine, but the orders may vary, n number of orders you may get it, but the variables are only limited to 4. So the problem is also like they are using this DNA structure for storing or manipulating the data, to collect the data, to develop the data, to predict the next also. Okay, so there is one issue called Adilman algorithm. What is this? We are going to use a directed graph with n vertices and designated each vertices input with output. And we have to generate first a random generation of the path. Then we have to go with the filtration. What the filtration? Reject all the paths that do not begin with in. Okay, so definitely it should begin with VIN, and the path should end in V out. This is what we say a path. Reject all the paths that do not involve exactly n, because you have a n vertices mean it has to start in between, it has to travel the path. So that should be that n minus 1. So if it is with all the n, you should not take it. There should be only one unique way. Then for each of the n vertices, we reject all the paths that do not involve v. Okay. So what happens is you have to reject the paths that do not involve v. So I'm coming to, where is the figure? This is example. That is V vertices simply as it is. I think they have given it. So, sorry, n vertices. What is the of the n vertices? This is the edge. This is the edge. What is the V? I think I forgot. Edges are the V in, V out, entry and exit. Sorry guys. V in, V out. Okay, the input and output, they have generally put V, it seems. Okay, so reject all the part that do not involve, because there should be one output or either the input should be given. Yes, if any path remains, okay, no otherwise. So the thing is that probably this is something, it's very similar. You have to generate a random walk, but you have to choose all the random walk according to the two conditions. Okay, so it should begin with the V in, it should end, okay, and it should not get all the vertices because it should have some kind of n minus 1 vertices. Okay, then every vertices you should have your input and the output because it should involve this V in and the V out. So if that condition satisfies, you put yes. If not, you put no. Okay, now this is one example from the city, how they are going to make it. So this is for the city, the DNA they have given one some sequences. Okay, but immediately they are writing the complement. For A, it is the T complement, G, the complement. But the problem is when Atlanta to Boston, this Atlanta to Boston, who is going to make this one? Now you have to make a common GCAC and TGAA. Sorry, Atlanta to Boston. Who is the Boston person? This one. So the tail and the head. Okay. So TCGC. This is the head of the Boston. This is the tail of the 1 minute. Sorry, ma. Okay, so this is your head, this is your tail. Okay, you are starting Atlanta to Boston. So this tail is going and it is going to get connected with the Boston. So the issue is like this is your transition, your flight number or whatever. Like this is like one character you are generating, and accordingly you are generating the complement, and you are also using the connection transition between this one, and you are producing a population. Okay, and from the population you are going to get a new string. So this is kind of you are going to work on the n number of possibilities. Okay, even this, it is, they cannot say this is a flight number, but this is one transition. Why they say this is a flight number? Because that only connects this one. So you must have learned it in some other your algorithm part, right? Every transition state, when you are able to make n number of possible transition state, and the best optimum transition is you can choose it. Okay, this is one just example. I am just explaining very randomly. Because in the last minute of the exam, I cannot go with all the previous steps actually. Whatever you should have it in imagination, I'm just taking. Okay, so the DNA computing problem, the people are working with similar to the traveling salesperson, this thing, and everything like a that highly depends upon the probability of that event and the probability of that state as well as the transition between the state as well as the output. All the three are really important in any search algorithm. See, we are learning different search algorithm. DNA computing is also one such search algorithm. Hidden Markov model is also one such search algorithm. Okay. So I'm just giving only the introduction. You please read this biological part of this DNA. You will read this. I will post this article, and the rest you ignore it because I'm preparing you guys for small questions of the exam. Okay, and you do good. And I'm sorry, like I'm not able to completely cover your this thing. Probably before the next semester or something, whatever the portions I leave it right now as it is, I will redo it. I will make sure that you have learned the complete algorithm portions. Okay, ma? And you don't regret that you have not studied this paper completely. I didn't expect that I will get this, what is that, corona issue. I'll stuck with this 1 month. I didn't expect, but it's an unexpected problem. So please adjust this time. No regrets. Okay. You can prepare only for the portions whatever I teach. See, today I taught something because I just want to take a couple of questions from these portions. That's what I took. So you study whatever I teach. Beyond that, there won't be any question. Okay, the portions which I have not covered this time, I will take after your semester exam. I will take a couple of classes. I will finish it. Is that fine?
Okay, ma'am.
Okay, ma'am.
Okay, Arnab okay, Amal okay. What happened to others?
Okay, ma'am.
Okay, ma'am.
Okay. You all are okay with this, right? And I'm sorry that my health made your study a little bit, you know. Okay, it doesn't matter. You can come out cope up. All the best.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Okay.
Can you please the slides?
One more thing is, yeah, I will share the slide now. And the thing is, one more thing is that who is making the attendance for me?
Ma'am, me and Hema.
Please, can you send the attendance for me?
Yes, ma'am.
Okay. To my Gmail address, I mean, Big PO address.
Yes, ma'am. Sure, ma'am.
Thank you. When will you send it?
Ma'am, by tomorrow we'll send it.
Okay. No problem.
Thank
Thank you
you.
so much. Thank you. Thank you.